It is now time to look at an example which deals with the normal and tangential components. So a car travels along the circular path such that its speed is increased by at is equal to 0.5 e to the power t, where t is in seconds. We need to determine the magnitude of its velocity and acceleration after the car has traveled s is equal to 18 meters starting from rest. Now that we have seen a couple of problems related to the kinematics of a particle, I'll give you a couple of minutes to try to solve this one on your own, and whenever you're ready to see the solution, just continue the video. So the very first step involves writing down what we know. So we have an expression for at as a function of time. We know the radius of curvature from the figure, which is equal to 30. We know the initial velocity, which is equal to 0 meter per second. And we know that the final position is 18 meters. We also have multiple equations. The first one, which is at is equal to dv over dt. The second one, which is an is equal to v squared over rho. And finally, the kinematic equation, which states that v is equal to ds over dt. Writing down in parentheses what we know and what we don't know, we have s, a, and an unknown. So to find an expression for v, we can simply make use of the equation that relates a to v. dv is equal to at times dt. And since we have an expression for at, it is relatively easy to find an expression for v. We simply need to do the integration. So from the left hand side, we got v minus v0 is equal to the integral of the expression of at dt. Performing the integration and taking that from t0 to t, we have 0.5 et minus 0.5 et0. And then noting that t0 is equal to 0, et0 is equal to 1. And so the expression for v is 0.5 et minus 0.5. So far we have an expression for v as a function of time, an expression for at as a function of time, and no values for an. Remember, an is equal to v squared over rho, so we need the value of v at the specific instant where s is equal to 18 meter. And so to get this value, we need to find the value of t, so we can replace that into the expression of v. To find t, we need to make use of the value that we have, or that we're given, and that's s is equal to 18 meter. So we know that the final position is s is equal to 18 meter, and we need to find the time at that position. So it makes sense to make use of that value. So to do so, we need to find an expression for s as a function of time, and we can simply remember that v is equal to ds over dt. Since we have an expression for v, we can write that ds is equal to v dt. Then taking the integration for both sides, we have s minus s0 is equal to the integral from t0 to t, 0.5 et minus 0.5 dt. Then performing the integration and taking that from t0 to t, we get an expression for s minus s0, which is equal to 0.5 et minus 0.5 t minus 0.5. Then noting that s0 is equal to 0 and that s is equal to 18, we only have a single unknown in this equation, so we can solve for t. Then solving for t, we get t is equal to 3.7064 seconds. So we have solved for t, we have an expression for v as a function of time. We can replace the time with 3.7064 to get the value of v at the instant where the car crosses 18 meters. We get v is equal to 19.85 meter per second. Now that we have the value of v at that specific instant, we can get the value of an at that specific instant by replacing in the expression an is equal to v squared over rho. Replacing all that and doing the calculation, we get an is equal to 13.14 meter per second squared. Now to get at, we have an expression of at as a function of time. We simply replace t with 3.7064 and get a value of 20.35 meter per second squared. Now finally, to get the magnitude of a, we simply have to take the square root of both components squared. So square root of at squared plus an squared doing all the replacement, we get A is equal to 24.2 meter per second squared. Again, it is very important to understand this methodology in which you look at the equations and see which equations would actually give you a single unknown which you can solve for. And that's the strategy you will use during the whole course. So it's very important to get used to it. You have the formula sheet with the different equations for the specific section or topic you're working on. You have the different variables that are given in the problem. So you have what you know and you know what you learned. You need to combine these two together and see which equation you can actually make use of. And remember, you can go up and down the ladder. So you can calculate V given A or calculate S given V by simply going up, which means integration. Or you can get A given V or V given S simply by taking the derivative.